This video is for section 18.3 about reversible reactions and equilibrium. The learning goals are to understand what happens at the molecular level in a chemical system at equilibrium and know three stresses that can cause a change to the equilibrium position of a chemical system. Let's look at that first learning goal. Understand what happens at the molecular level in a chemical system at equilibrium. Almost every chemical equation we've seen this year has had an arrow that has pointed to the right only. But in reality, many reactions can occur in the reverse direction. To show this in a chemical equation, you use a double arrow. A reversible reaction is a chemical reaction in which the conversion of reactants to products and the conversion of products to reactants occur at the same time. Here's an example reversible reaction. 2 moles of SO2 combine with 1 mole of O2 to produce 2 moles of SO3. Notice the double arrow, however, showing this is a reversible reaction. What that means is at the same time that forward reaction is creating SO3, the SO3 is decomposing to create the substances on the left side. Let's consider that this example reaction happens in a closed container. And at the beginning, there's going to be a lot of SO2 and O2, but no SO3. Because the reactants are highly concentrated, the forward reaction will occur at a quick rate. But as the SO2 and O2 are used up, the forward reaction will slow down. At the same time, as the amount of SO3 is increasing, the reverse reaction will start to happen. At some point in time, the rate of the forward combination reaction will be equal to the rate of the reverse decomposition reaction. That point in time where the rate of the forward reaction is equal to the rate of the reverse reaction is called the equilibrium point for the chemical reaction. Chemical equilibrium is a state of balance between the rate of a forward reaction and the rate of a reverse reaction. At chemical equilibrium, both the forward and reverse reactions continue, but because their rates are equal, there's no net change in the amounts of the reactants and products. Therefore, chemical equilibrium is a dynamic state, not a static state. That means that the reaction continues to happen. The forward reaction creates the products, the reverse reaction creates the original reactants. That's continuously happening, but there's no net change in the amounts of reactants and products. The equilibrium position of a chemical reaction refers to the concentration of the reactants and products when the reaction is at equilibrium. Here's an example. A reaction converts A into B. It's in equilibrium when the mixture contains 10% A and 90% B. Write this with a chemical equation. So we know a chemical equation uses an arrow in the middle to separate reactants and products. The one reactant here is A, and the A is changed into B. That's the equation we're used to seeing. However, this equation is reversible, and you show that with a double arrow. And then, to show the equilibrium position, one way is to write down what percent of the overall substances is reactant A, and what percent of the overall substances is the B. Another way to show this is to write down A changes into B, and then for the reversible reaction, to draw the arrow shorter than that first arrow. That indicates that the product B is favored. At equilibrium, it's going to make more of substance B than what there is of substance A. Example 2, a reaction converts C into D. It's in equilibrium when the mixture contains 85% C and 15% D. Write the equation for this. So C, and then an arrow, and then D. Because this is a reversible reaction, make it be a double arrow. And then to show those relative percentages, you can write them underneath. The alternative way to show this is with the double arrows, but make the arrows different size. So C, and then the arrow to D, but the arrow back to the left, you want it to be longer, because at equilibrium, it's the reactants on the left side of the equation that are favored, meaning there's more of them at equilibrium than there is of substance D. The second learning goal, know 3 things that can change the equilibrium position of a chemical system. These things are called stressors. They affect the equilibrium position. That is, they cause changes to the concentrations of the reactants and products. One of the stressors is exactly that, changing the concentrations of the reactants or products. A second stressor is to change the temperature of the chemical system. And a third stressor is to change the pressure that the system is under. There's a rule that we follow to figure out what happens to the equilibrium position when one of these stressors is applied to a chemical reaction. The rule is called Le Chatelier's principle. If a stress is applied to a system that's in dynamic equilibrium, the system changes in a way that relieves the stress. Now let's look at some examples to see what that means, to relieve the stress. Here is an example chemical reaction. Hydrogen carbonate changes into carbon dioxide and water. Notice the reversible reaction. The carbon dioxide and water is changing into the hydrogen carbonate. Now, what will happen to the equilibrium position if carbon dioxide is added to the system? What will happen if you had a container in which this chemical reaction is occurring and more of the CO2 is put into the container? How's the chemical reaction going to respond? Well, it needs to relieve that stress. So to relieve adding more CO2, it needs to use up that CO2. CO2 is used when the reverse reaction happens. CO2 gets used by combining with water to make the H2CO3. So what happens to the equilibrium position? It shifts to the left. The CO2 is going to get used up, creating more H2CO3. That is, the concentration of the H2CO3 is going to increase. Increasing the amount of the stuff on the left side of the reaction means that the equilibrium position has shifted to the left. Another way to say this is that the reaction will favor the formation of the reactants. Remember, on the left side of the arrow, the stuff that's over here is called reactants. So if the reverse reaction rate increases to overcome that stress, it's going to favor the formation of the stuff on the left side of the reversible reaction. Number 2, explain what happens to the equilibrium position if CO2 is removed. So how will the chemical reaction respond if some of the CO2 is taken out of the container? It needs to replace that CO2. The CO2 is created when the forward reaction occurs. So the equilibrium position will shift to the right. Saying that the equilibrium position shifts to the right is another way to say that the forward reaction needs to kick into gear to create some more CO2 to replace what was removed. An alternative way to say this is this favors the formation of the products, or favors the products. Short way to say that. Number 3, what happens to the equilibrium position if H2CO3 is added to the system? So what happens if more of this is added? The chemical reaction is going to respond by using up the H2CO3. H2CO3 is used when the forward reaction happens to create these products over here. So it shifts to the right. Another way to say shifts to the right is to say it favors the products. Here's another example. N2 plus 3H2 produces 2NH3 plus heat, and the double arrow indicates it's reversible. So the reverse reaction is happening at the same time. Now question 4, explain what happens to the equilibrium position if heat is added to the system. Well, where is heat? Heat's over here. Heat's on the product side of the equation. What if more heat is added? The chemical reaction will respond by using up that extra heat. Heat is used when the reverse reaction happens to create the stuff over here. So the equilibrium position will shift to the left. The reaction will favor the reactants. Explain what happens to the equilibrium position in that reaction if heat is removed. Well, what if the heat, which is over here, is removed? The chemical reaction will respond by trying to replace that heat. Heat is a product of the forward reaction, so the equilibrium position will shift to the right. The chemical reaction will favor the formation of the products. If a chemical reaction involves reactant and products that are gases, then changes in pressure can affect the equilibrium position. Here's an example. N2 plus 3H2 produces 2NH3, and that happens in reverse. Number 6, if the volume of the container enclosing the reaction is decreased, then the pressure will increase. Explain what happens to the equilibrium position when pressure increases. Le Chatelier's principle says that the chemical reaction will respond by alleviating that stress. So how does the chemical reaction alleviate the fact that pressure has increased? It needs to do something that will decrease the pressure. So to decrease the pressure, the reaction needs to create fewer particles. If there's fewer particles in the container, then there will be less pressure. So let's pay attention to how many particles we have here. Let's take a look at the left side of the reaction first. This says there's 1 mole of N2 plus 3 moles of H2. Adding the coefficients, there's 4 moles of particles colliding with each other. Okay, over here on the right side, there's only the 2 at the beginning here, so there's 2 moles. Which side of the equation has fewer moles? Well, that would be the right side. So to reduce the pressure in the container, the forward reaction needs to pick up to change 4 moles of particles into 2 moles of particles. The equilibrium position will shift to the right. Number 7, if the volume of the container enclosing the reaction is increased, then the pressure will decrease. Explain what happens to the equilibrium position when pressure decreases. Le Chatelier's principle says the chemical reaction will respond by alleviating that change. So to alleviate the decrease of pressure, it needs to do something that will increase pressure. To increase pressure, the chemical reaction wants to create more particles. Well, it's the reverse reaction that creates more particles. The reverse reaction takes 2 moles and changes it into 4 moles of something. So the equilibrium position will shift to the left. Another way to say that is the reactants are favored. Observe that in the case of pressure changes, the way that the stressor is relieved is by increasing or decreasing the amount of particles in the system. So you want to pay attention to the coefficients of the equation to see the relative number of particles on each side of the arrow. Now for some check for understanding questions. A reaction has this equation. Notice it's a reversible reaction. How is the equilibrium position affected by each change? I'll pause the video for you to answer A, B, C, and D, and then we'll check. Okay, here's the answer using the lingo shifts right or shifts left. Okay, so what happens if the temperature is lowered? The system will respond by doing something that will raise the temperature. It's going to make more heat. Here's where heat is located. It's a product of the forward reaction. So to make more heat, we want the forward reaction to increase in pace. The equilibrium position shifts to the right. Okay, question B. What happens if pressure is decreased? The chemical reaction needs to increase the pressure. So it needs to create more moles of particles. The left side has 2 plus 1 makes 3 moles. The right side has 2 moles. To make more moles of particles, the reverse reaction needs to increase its pace. So it shifts left. Okay, what happens if oxygen is taken out of the container? Well, the chemical reaction needs to respond by making some more oxygen. Oxygen is located right here on the left side of the arrow. So if the reverse reaction happens, it's going to make more of the oxygen. So the equilibrium position shifts to the left to create a greater concentration of oxygen. Okay, what happens if sulfur trioxide is added? We'll find where that is. Here it is, sulfur trioxide. So the chemical reaction will respond by using up that extra sulfur trioxide. Sulfur trioxide is used when it combines with heat to create the stuff over here on the left. So if we want to use up sulfur trioxide, we need the reverse reaction to pick up. So the equilibrium position shifts to the left. Now number 2. A chemical reaction has this equation. How is the equilibrium position affected by each change? I'll pause the video for you to answer A, B, C, and D. And here are the answers. So if temperature is lowered, the reaction will respond by doing something to raise the temperature. It's going to make heat. Here's heat. Heat's on the left side of the reaction. So the reverse reaction needs to pick up. It shifts left. Okay, what happens if pressure is increased? The chemical reaction will respond by doing something to decrease the pressure. It needs to make less gas particles. On the left side, there's a 1 right here in front of the gaseous H2O. On the right side, there's a 1 here, there's a 1 here, so in total there's 2 moles of gas particles. The left side is the one with fewer moles, so the reverse reaction needs to pick up. It shifts left. Question C, what will happen if hydrogen is removed? Well, the reaction is going to attempt to replace that hydrogen. Here is where hydrogen is located. It is a product on the right side. To make more of that hydrogen, the forward reaction needs to increase. It shifts right. And what happens if water vapor is added? Well, the reaction will respond by trying to get rid of that extra water vapor. Here's where water is located. The reaction needs to use up the extra water. So water is used when the forward reaction changes it into this stuff. So the equilibrium shifts to the right. This concludes the video about equilibrium positions and Le Chatelier's principle.